Professor Nicola Cavalagli. Please, Filippo.
Thank you, Carmelo. Yeah, this is a little bit unusual, but when we received this invitation, we decided to do it jointly, honestly because Nicola is the person that leads most of the experiments on masonry we do in our group, so this was the right way of presenting the work. So I will introduce a little bit what we will present you, then give the speech to Nicola, and then I will close at the end with something a little bit new that I would like to present. So the topic of the workshop is very broad and actually very nice topic, and thank you, Paolo, for the invitation. So we were uncertain about what to show. So we did this kind of scientometric analysis to look for keywords, right? And what we discovered is that if we use the main words of this workshop, we find 4 clusters of works. There are works on remote sensing and radar and SHM, of course. There is a second cluster which is grouping works on ground penetrating radar, so mostly non-destructive evaluation, infrared thermography, inspection, and also photogrammetry. And then there is another cluster that is more on ambient vibration tests, model analysis. This is more or less where we fit more at University of Perugia. And then a 4th one on numerical methods, finite element analysis, and so on. So we were saying, so what should we show? Which cluster should we frame in? And so we decided to show a little bit of everything. When you don't really have something, focused, this is what you do. You show a little bit of everything, right? So we will show 3 experiences that will be two case studies where you will see OMA, you will see NDE, and then we'll show a little bit of numerical simulations, especially with thank you, with the applied element methods for simulating collapse in arch bridges. And this will be presented by Nicola, and I will close with a couple of minutes presenting some ideas we have for something it's not in the clusters you have seen before about how we could monitor arch bridges in the future in a way that we can call smart.
Okay, now we can go more in depth in this analysis and in this experience that we had. And the first case study is the Lucano Bridge that is located in Tivoli near Rome. This is it is an old Roman bridge, and this is a particular bridge because it's located in an archaeological Plauzi mausoleum, in an archaeological site. The mausoleum that you see here in this photo is an old photo, now is restored a couple of years ago. And another particularity is that this configuration that you see in this picture is new, but the bridge has in the original asset constituted by 5 arches. And now you can see only 3 or 4 arches because the other arches in the west abutment now is covered by the bank river, because after some urbanistic plan, they have been covered and the river bed has been reduced. And you can imagine that this kind of situation could raise the risk of flooding in some situation. So, which is the object of the research? As already Filippo introduced, we have applied some non-destructive tests after the geometrical survey made by UFV photogrammetry, and in particular in this case we have applied infrared analysis, so thermographic images, and also GPR. By using the geometrical survey through photogrammetric techniques, it was possible to obtain a point cloud and also a texturized model that has been used to do material survey, visual inspection in details, and in particular also material degradation survey that has been carried out by using an automated procedure based on digital image processing, and also after the first automated processing, also another manual processing to improve the material degradation survey. So it was possible to divide the presence of black rust, biological patina, and similar situation. These are some images related to the thermographic inspection. The idea is to find some correlation, okay, to improve the knowledge of the bridge. It's called qualitative knowledge that can arise by using this kind of analysis. And obviously, we have performed this inspection in different days, different times of a day. And what we have seen is that in this side, for example, we have hot areas that are concentrated in this part, and cold areas that are concentrated in this abutment. And here we can see that in the right side of the slide, a particular sketch of these images on which we can also observe that these cold areas are also related to the presence of biological patina, so that allows us to say that we have humidity, presence of water, and so on. And then we have the results of the ground-penetrating radar investigation. As you know, the antenna of the radar can be installed in a machine like this, in which we have also metric wheel. And when you go to a point A to a point B, from a point A to a point B, you can obtain a radargram that is something like this, that allows us to recover some information that are not visible. For example, the most rapid information that you can observe is the presence of the metallic grid of the pavement. In this case, it was possible to recover also the old arches in the west abutment that now are covered by the soil, and other objects that are not so clear, but in this case, we were out of the bridge. Another aspect that was interesting, and that we can more in depth in the next slide, is the presence in this area of an attenuation of the signal. So this is the comparison, a qualitative comparison of these results. In particular, in the left side, we can observe a comparison between the degradation material survey maps and the thermographic images. For example, we can observe a correlation between the presence of black rust degradation with the hot areas that we have observed before. And on the other side, in the right side, the presence of the cold area with the vegetation and the biological patina that we have already mentioned. These aspects have been already investigated more in depth with the comparison between these thermographic images and the GPR radargram, because the presence of the attenuation of the signal that we have mentioned, in fact, corresponds to the presence of the lower level of temperature. So this aspect effectively is confirm the presence of water in the backfill of that side of the bridge that could be considered also in the next intervention of restoration that could be made in the bridge. The other case study is an old masonry bridge that belongs to the High Middle Age. It's located in Todi, is a small town in the center of Umbria region, and as you can see, it was severely damaged. Today has been restored. Is restored, so the configuration is dramatically different. And the approach, by considering the clusters that we have introduced at the beginning, now we have performed some ambient validation tests for the calibration of numerical model, finite element modeling. At the beginning, we have performed, as we have done before, the digital survey by using, in this case, both terrestrial laser scanning survey and also photogrammetric survey. Also by seeing a comparison of these 2 point clouds. And we observed that the resolution that we can obtain by using only the photogrammetric survey is really enough, with a high precision for the engineering purposes that we need. So we have performed the ambient vibration test by using piezoelectric accelerometers. We had 9 uniaxial high sensitivity accelerometers that we have used in 3 different setups to catch the vertical and also horizontal out of plane direction of vibrations. And we have estimated the first natural frequencies of the structure and the related mode shapes. The first one in this case was out of plane, the classical out of plane that we can expect. The second one is the first antisymmetric in plane mode shape, and then the third is the out of plane, and then again the fourth is the in plane symmetric one. This order of the, as you know, probably know, the order of these classical mode shapes that you can expect in the masonry bridge. It depends effectively by the structure, by the geometry, by the boundary condition. And as introduced in the first presentation of this morning by Professor Gentile, the possibility to have the knowledge regarding the geometrical aspect of the structure, in particular in this case by considering the damages that we had, is really important, because I don't report here, didn't report the results that we have obtained by using a more simplified model, not considering all of these damages. But in the simplified model, it was really impossible to catch this order of the mode shapes, because these damages that we can observe here affect dramatically the order of the mode shapes. It's not a problem of calibration in terms of materials, but only the mode shapes. So by using a manual calibration, so it was possible also to calibrate this model, and then to use this model for seismic assessment and other models. Concerning the numerical modeling, we have in these last years, we are using also this other approach, that is the applied element method, that consists in dividing the structure in a finite number of volumes that are connected by using springs in normal and tangential direction, and on which are condensed the material properties that could be also with nonlinear constitutive models. This is an application that is not applied to a masonry bridge, but is the well-known Albiano Magra bridge that collapsed on April 2020, and we decided to show this slide because the use of another non-destructive techniques, that is remote sensing, by using the synthetic aperture radar sensor, the satellite radar, SAR images. It was possible to know which could be the deformation that a structure are going on. For example, here you can see that these points are persistent scattered point detected by the satellite consistently, and you can see here in this part some anomalies simply in the color. In fact, in the month before the collapse, this was the deformation that can be represented in the structure, and we can see that something of anomalies were happening in this side of the structure. In fact, we know that there was a landslide on the right side that was pushing the structure until the collapse. This kind of analysis, if combined with a numerical collapse simulation, make it possible to, in some cases, but it depends, it's possible to prevent or maybe to know which could be the time to failure by combining these two kind of information. So the last step was that we have tried to apply this numerical method also to masonry structure. This is the well-known Prestwood Bridge. The model was calibrated by using the information that are reported in the page report, and also that we can find in other papers that is in the literature, and we obtained consistent numerical results in terms of both collapse load and also collapse mechanisms.
Thank you, Nicola. So going to the end, we know what is the difficulty in monitoring masonry structures. We know they're complex, we know they're non-linear, we know that we have limitation in aesthetics and many other problems, wirings and so on. So what I'd like to show at the end is an idea we have to basically challenge an axiom that we have in the SHM community. It's written in the book by Professor Ward and Professor Farrar, that sensors can never measure damage. So the question is, can we achieve a more direct to damage to decision link in masonry? So this was the idea we proposed in a project that has just been funded by the Italian Fund for Science, which is the Italian equivalent to the ERC. This is a advanced grant of this scheme. It has started a few months ago, so I have no results to show about arch bridges, but I want to give you the overall idea. So the proposal here is to retrofit masonry structures in such a way to make them be able to self-monitor their damage conditions. And the way in which we're proposing to do that is by developing what we call smart bricks. This is a smart brick. It looks like a normal brick, but its micro and nanostructure is modified such that it becomes a sensor. Here you have the load applied on the brick, and here you have the strain measured with electrical strain gauges, and here you have the electrical response coming from the brick itself, which you see it's a pretty good strain sensor. But not just the brick, we would also like to retrofit the masonry structures and use a special mortar in critical locations within the structure, such that the mortar becomes directly damage sensing, not strain sensing, but directly damage sensing. Here are some results on these smart mortars we are developing these weeks, actually, where you see that basically we have a reduction, a continuous reduction in the electrical conductivity. The mortar is also nano-engineered. A continuous decrease in the electrical conductivity with the increasing tensile damage in the mortar. And of course, the more this curve becomes, shows a strong jump with small damage values, the more we are able to automatically detect a crack before the crack is visible by human eye. This is the idea, or by a photography. So there are no conclusions because it's a lot of different things, just a little bit of stimulation. And with this, we thank you very much for your attention, and we thank the funding of what you've seen at the end. Thank you.
Thank you. I think that there is time for a very quick question. Yeah, there.
Thank you for the presentation, very interesting. Regarding the last part of the speech, you talk about nano bricks and nano mortars. Which kind of nano composite did you use for making this?
Yeah, thank you for your question. First of all, this is a 5-year project. It's just started, so there will be a lot in the future. And maybe something on an arch bridge like the one that Vasily has shown. Regarding your question, for the mortars, we use mostly carbon-based nano inclusion. So we are using carbon nanotubes, but we are also using carbon nanofibers, also something micro, like microfibers. But the thing is that if you want to be able to detect the crack when it's a micro crack, you need the conductive fiber to be very short. Otherwise, you have bridging effect. So you will see the crack when it's too large. Regarding the brick, carbon is difficult to use because carbon burns, basically, when you burn the brick. So we are working on burning the brick in nitrogen, and we are working with some colleagues from chemistry to try to keep carbon into the brick. This is really difficult. So what you have seen now is based on the use of steel microfibers, so metallic fibers. Difficult to disperse, though. So the production of the brick is really complex. Thank you.
Okay, thanks again. And let's